You know what? Before I jump into that, I'm gonna resume this now, right? So we're gonna be talking about a normal approximation to the binomial distribution and to the p-hat distribution. Cool stuff, right? So the probability that a new vaccine will protect adults from cholera is known to be 0.85. The vaccine is administered to 300 adults who must enter an area where the disease is prevalent. What is the probability that more than 280 of these adults will be protected from cholera by the vaccine? This question falls into a category of a binomial experiment, right? With the number of trials n equal to 300, the probability of success p equal to 0.85, and the number of success r greater than 280. So it is possible to use the formula for the binomial distribution to compute the probability that r is greater than 280. However, this approach would involve a number of tedious and long calculations. There is an easier way to do this problem, right? So for under the condition stated below, the normal distribution can be used to approximate a binomial distribution. All right, so let's take a look at how that works. This is real easy, real interesting. All right. I want to start off by giving y'all some formula real quick. The homework for this section is already posted, so y'all can take a look at it. It's a whopping one question. Yeah. All right. So here's the formulas for this, right? So we have our normal approximation to the binomial distribution. Consider a binomial distribution where n is our number of trials, r is our number of successes, p is our probability of success on a single trial, q is our probability of failure, which is written as 1 minus p, right, on a single trial. Now, here's what's key, right? If n times p is greater than 5, and n times q is greater than 5, then R has a binomial distribution that is approximated by a normal distribution, with mu equal to n times p and sigma equal to the square root of n times p times q. Note, as n increases, the approximation becomes better. All right. Since I am recording this and I'm putting this to YouTube land, I'm going to ask a question to YouTube land, right? Because something that I personally don't understand, right? Why does n times p have to be greater than 5? I have no idea. All right. So if y'all ever like in the future look back at this video and y'all figure out the reason, right? Type it in the comments section. Let me know for my educational benefit, please. All right. I'm just curious. I have no idea why. I'll be honest with you. I don't know, but I would like to know. I would like to know. All right, all right, all right. So let's take a look at this real quick, right? This is going to be real cool. What is it called? So this is an approximation to a binomial distribution, a normal approximation to a binomial distribution. So let's look at this example right here. We have the binomial distribution graphs. So the graph of the binomial distribution for P equals 0.25, where Q is equal to 0.75, and the number of trials is first n equals 3, then equals 10, then n equals 25, and finally n equals 50, right? Here's how that looks right here, right? So the authors use a computer program to obtain this binomial distribution, right? Long story short, this is one of those questions where, like, if you have a calculator, it'll take you to heaven, right? But what if we don't have a calculator? How did people used to do this back in the day? That's what we're talking about right now, right? So right here we have our n is equal to 3. Our probability of success is 0.25. Our probability of failure is 0.75. Right? We have a mean, which is n times p, which is 0.75. And we have our standard deviation, which is the square root of n times p times q, which is 0.75. Right? So boom, there we go. Now, when we approximate this to a normal distribution, which is what you're seeing in figure 732, right? So we're going from 0 to 7, right? Everything after 7 is just 0. Remember when we're doing the binomial distribution, how like some of the numbers towards the end would just be like 0, 0, 0, 0, 0? That's what this is right here, right? So what I'm trying to say is that whatever question you ask me, right, rather I could find the exact answer using the old method, right? That's what figure 731 is showing you, right? So I could ask you like, oh, what's the probability of two? And then you could just look at it like, oh, 0 point, I don't know, 15 or whatever, right? Or right, I can use the normal distribution to approximate what it would be, right? So this is what we're learning today, how to approximate an answer, right? And you have one homework question that you get to do for that. It's awesome, right? I'll show you when I get to an example. You have two ways. You could do it the old way or you could do it approximated way. Yeah. There's a way to turn the binomial distribution into a normal distribution, and that's how, right? So right here, first thing you have to do is you have to verify that when you multiply n times p, the answer that you get is greater than 5. And also when you multiply n times q, the answer is greater than 5. Only then can you use the normal distribution to approximate the what you call it, the binomial distribution, right? So over here, n times p is 6.25, so we're good to go, right? You have your x is 75. Can't complain, right? Now you see with a question like this where n is 50, this is where we want to use a normal distribution to approximate it, right? I want y'all to look at something, right? This is n25. You see how many bars there are here? And then you see with n50 how many bars there are? Look at how close the bars are to the red line in N50 compared to N25, right? So what I'm trying to say by that is that as N gets larger, right, we get closer and closer to what the normal distribution would be, right? It becomes a better approximation when N is like stupid large. The higher the better. Right. The higher it is, the better. Mhm. So when n equals 3, the outline of the histogram does not even begin to take the shape of a normal curve. But when n equals 10, 20, or 50, it does begin to take a normal shape indicated by the red curve. So from a theoretical point of view, the histograms in 732 and 733 and 734. So this is 732's histogram, 733, and 734, right? They would have bars for all values of R from R equals 0 to R equals N, right? However, right, in the construction of these histogram, the bars of heights less than 0.001 unit have been omitted. That is in the example probabilities that the less than 0.01 have been rounded to 0, right? So remember, with a normal distribution, right? The tail ends, right? This never actually touches the x-axis, right? We never actually get to 0, but we get really close, right? Really close. So this is why you can use it to approximate it, right? Pretty cool. So you would, if I asked you a binomial distribution question, but then the n is just stupid big, right? Like it's, yeah, not flat, but I'll give you an example. Like Mm-hmm. It would be. Hold on, let me get y'all in 1 second to figure out where this is. So what I'm saying is that the n is so big that remember our binomial distribution tables? Yeah. This thing right here, right? N is 2, 3, 4. N is so big, it's not even on the binomial distribution table. Like our tables only go up to 20, you know? So what do we do after that? Okay. Yeah. Well, we do what we're doing now. Yeah, we do what we're doing now. Oh, whoops, I forgot to switch it back 1 second. This is 7 still.
So on the homework, you said that the Thursday was
Mhm.
7, 8, 9.
7, 8,
That
9.
includes 7.1 to 1.2.
All of that. Yeah. Yeah. I don't make up questions. I copy and paste. Yeah. But you see, like exam 4 though, I'm making that up. It's gonna be real. If
Bring my notes. Can I do that?
you think it'll help.
No.
Mhm. All right, so let's look at this normal approximation, right? So the owner of a new apartment building must install 25 water heaters. Damn. From past experience in other apartment buildings, she knows that Quick Hot is a good brand. A Quick Hot heater is guaranteed for 5 years only. That sucks. But from the owner's past experience, she knows that the probability that it will last 10 years is 0.25, right? So, what is the probability that 8 or more of the 25 water heaters will last at least 10 years, right? So, define success to mean a water heater will last at least 10 years, all right? You can. That's one way of doing it.
You find
Right?
it be in the.
Right. That's the issue that we have right here, right? So let's take a look. That don't sound good. Doo, doo, doo. So, mm. So look, we want 25 water heaters, right? So what do I know? I know that N
25.
is 25, right? Past experience, blah, blah, blah. That's 5 years. Sample size, right? It's guaranteed for only 5 years, but the probability is okay. So our probability of success, right, is 0.25, right? So there we go. So our probability of success P, that's the 0.25, right? Now, what is the probability that 8 or more of the 25 water heaters will last at least 10 years? So they want to know what's the probability of at least no. I'm sorry. Wrong thing, right? They want to know what's the probability of 8 or more, right? What's the probability of 8 or more? Let's turn that into math, right? They want to know what's the probability of R, right? Greater than or equal to 8. We agree? Right? All right. So now, problem I have is that n is way too big. It's not even on the chart, right? The first thing I want to do is I want to verify, right? Is n times p greater than 5? I'm putting a question mark here because I don't know if it is. All right. So 25 times 0.25. So you said 6.25, right? All right. Let's put a check mark because we're good, right? Next thing I want to verify is n times q, which remember q is 1 minus p, right? Is that greater than 5? I don't know if it is. Let's check it out, right? So this would be what? 25 times 1 minus 0.25. Is that greater than 5? That's 25 times 0.75.
What the hell is happening here? Hold on.
Right? I just want to know, are they bigger than 5, right? They have to be bigger than 5 for me to do this approximation.
The first one is
Mhm.
0.7.
So what's 25 times 0.2075?
Yes.
Really?
25 times 0.25.
No, times 0.75.
It's 18.5.
18.5?
18.75. Yeah, 18.75.
Okay. All right, so we Gucci then, right? So we can actually use this to approximate a normal distribution, right? All right. Let's think about this for a second. Let's say I change that R to an X, right? Kind of starting to look a little bit more familiar, right? All right, I changed that R to an X, right? What am I going to change the X into that I know how to do? I always change my X's into no, it's not a letter. No, a letter. Z, all right? So the next thing, this is going to become probability of Z greater than or equal to, what's that Z formula again? X minus mu over sigma, right? Huh? Normal distribution. Right. Mu, population mean. Yeah. It's on the formula sheet. Yeah. You don't gotta memorize it. It's on the formula sheet. Right? Mean. All right. Same thing. Same thing. Now, let's think about this for a sec. I know what X is, right? Simple. What's X? What am I gonna write there?
What, 18?
No. What's next to the X? What number?
8.
8, right? But what's my mean?
18 months.
No. For a binomial distribution, how do I find the mean? No. What's the formula for mean in binomial distribution? It's in chapter 6.
At the time,
Go down.
all equal
No, go down. The other one.
U equals 1.
No, go down.
Oh, U equals MD.
That's it. All right. So my mean, all right, is equal to n times p, right? And in this case, my n is what? 25 times my p, which is what? 0.25. Somebody told me the answer earlier. They said it was 6.25. So all I gotta do is write that in. Easy, right? Now, standard deviation, right? What's the standard deviation formula? So sigma equals square root NPQ, right? All right. Just plug in the numbers, right? NPQ. The standard deviation
Yeah, that's those,
right?
that's zero meaning.
Sigma. It's a population standard deviation. Yeah.
P is 0.15.
N times P,
Q.
what's the parentheses?
Parentheses RP.
N times P times 1 minus P. Yeah. And then what's that answer? I'm gonna do it on my end also just to verify y'all get it right. All right, what y'all got?
4.6875.
Let me see. I got 2.165.
That's 25 times 0.25.
Then times and times 0. Yeah.
125?
I put 0. I didn't.
All right. So that's the 2.65064, whatever. All right.
Wait,
See.
25 times 0.15.
Mm-hmm.
Professor, that's not what I got.
Maybe there.
0.15 times 0.15. 4.60.175.
I got 6.
Did you square root it? Yeah. Mhm. That's what the check line on above means.
That's. How do you get that again?
Second square root.
Okay, now.
Now you got it? Awesome. So now I got probability of Z is greater than or equal to, after I do all the math on this, 0.8829. Right? Yeah.
Divider.
Mm-hmm.
I left my calculator all day.
Got you.
So that's the answer?
No.
No.
What do I do when I find a Z?
Oh my God, it's a long math.
It's too long. Yeah.
I mean, you got the first 8 0 8 2 okay, here.
Mm-hmm.
P, D, 3, plus 1.
All right, now what do we do?
You tell me what happens when you find a Z.
You plug it in
Okay.
somewhere. Times 5,
No.
that's the times.
You
There you go.
It-
We'll figure out 8
it,
of them.
it involves something I always tell y'all to look at. Oh no, we're done with 8. Not divide. You want to
And the square root of them.
how do I find probability for normal distribution? What do I do?
The P times.
And after you find the Z, what do you do with it? You look it up in the
On the point.
right in the table,
Table.
and then you get the answer, right? Mm-hmm.
After you get the B, you come here.
Right, the normal distribution table.
8.
So remember, we have to round this off, right? So I'm going to round this off to 2 decimal places, 0.81. All right. Now, remember, I can't look this up in the table because it's greater than. And my table only gives me less than, right? So I have to do the complement of it to look it up, right? So this is going to become what? 1 minus the probability of z less than or equal to 0.81. This you could look up, right? So this answer will be, because I can't look up greater than in the table, I can only look up less than, right? So this is going to be what? 1 minus 0 point something. Y'all tell me, what is the answer?
Table 8.
The normal distribution table. I forgot the number. It's the one that says normal distribution on top. Yeah.
What it be?
Mhm.
1.7910.
Point seven what? 7910. Okay, okay. Let me verify that it's right.
Do you see that? What are we looking for? Number 8?
So 0.81.
Okay.
So I'm gonna verify if that's right. 0.81.
We go to
So you go to the positive table, go to 0.8, and then 1. What'd you say it was?
0.7.
Good job.
Where do you see that?
All right. So we have a 0.8 right here. You have the 1 right up top. Look at where they intersect that. You have the 7910. All right. Boom. After this, a little subtraction, boom, 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 and we good to go. Mhm.
So from the 1 minus p
Uh-huh.
times z is less than or greater to 0.81, right?
Uh-huh.
Like she said, how do you go, oh, because of the decimal?
Yeah, so 0.8 is a z, and then at the top of the page is the 100th place. So you go to the 1, and where do they intersect that?
You go to the 1 here,
Yeah,
so 0.7910.
right. After that, little subtraction, nothing crazy. 1 minus 0.7910, and then we get 0.209, right? Now here's what's funny now, all right? Let's say we did this the old school way, right? Bless you. Let's say that we used our calculator to get the answer, right? Let's try it in the calculator real quick, just to see what answer the calculator gives us. Because remember, we're approximating it, right? So bear with me 1 second. I'll try and get my calculator. As soon as I figure out where I left it. Okay. I'm gonna show you guys something interesting now. All right. Good. Don't mind all my chicken scratch that's on there. All right. I'm just gonna verify the answer that we got real quick, all right? So we want to do 8 or more, right? Same thing with the calculator, right? It can't do greater than, so I have to use the complement of it, right? So I'm gonna do 1. Oh shoot. I messed up. Come back up here. Let's try it again. All right. So I'm gonna do 1 minus, and then what do? I go to the distribution, right? I'm gonna go down to binomial CDF, right? My n we said was 25. My probability of success we said was 0.25, right? And I want to know, right, 8 or more. So, and I can't do greater than, so I'm gonna do less than. So that's gonna be, I'm looking for 7, 6, 5, 4, 3, 2, 1, 0, right? So I'm gonna add all of those together, and I'm gonna subtract it from 1. Yeah, I'm looking. So right now, what I'm looking for is the actual answer. Let's look at our actual answer, right? So our actual answer that we got is 0.273937886. Our approximated answer was 0.209, right? That's not really so good, right? So this is our approximated answer, right? And then this is the actual answer. Right? Is 0.2739. I'm just gonna cut it off right there. 4. Right? Just got ran out of space.
The meat is, right?
Yeah. Mhm. So if we look at this actual answer and the approximated answer, that's not a really good estimation, right? So what do we have to do whenever we're trying to use a normal distribution to approximate the binomial? We have to adjust it a little bit, all right? We have to adjust it a little bit, all right? So because I want to go greater than, right, I have to go about half a step to the left. Let me not negative, but let me show you what I mean. Let me show you what I mean. What I'm trying to say is that this is a good answer, but it could be better. That's what I'm trying to get at. But I feel like we could use the practice in normal distribution, so I don't mind this. So what I'm trying to say, our mean, I forgot. What was the mean? It was 6.25. And I was looking for 8. Yeah. Mhm. I got you. I got you. Look. So what I'm trying to say is we have to take half a step back, right? So instead of 8, I want to do 7.5. So yes, I want this area here, but I want to accommodate for a little bit extra area here, right? That will make it so that my answer is a better approximation, right? So instead of the 8, I do 7.5. So let's look at that. I want to do the probability of X greater than or equal to, of course, 7.5. Let's try this now. I feel like this will be a better approximation because you see what we got, 0.209, that's okay. But the actual answer is 0.2739, right? Or like 27%, right? I feel like we could get closer to that 27% by up. Yeah, you want to be really, really close, you know? There's too much error in that answer, you know? You know how to do it in the calculator already from the binomial. Yeah. What I'm trying to show you is another way that you can do it if you don't have a calculator. All right.
Go the other way.
Huh?
Go the other way.
Yeah.
You accept the answer. Go
Mhm.
further.
So let's approximate this to z, right? So this is going to be z greater than or equal to what? X minus mu over sigma. We're essentially doing the same problem all over again, but this time instead of 8, we have 7.5. What's my mean again? 6.25 over the standard deviation, which is something 2.6165. 2 point what again? I just said it, but I forgot. 165. Yeah. All right. Let's do a little math on that. All right.
Five.
What you got?
7.5.
Say it one more time, sorry.
Definitely 7.5.
7.5, yeah. 1 sec.
1.25.
0.5775.
Close enough. I got,
0.5776.
yeah,
7.2.
57735. That's what I got. 3.6 is good too, right? Let's round it up to what? Good. All right. Before you look at it though, what's wrong with this? All right. Gotta do the complement. So 1 minus the probability of z less than or equal to the 0.58.
Okay, wait.
Sorry. This is gonna be 1 minus 0 point something.
0.58.
Mm-hmm. So now what do you do with that?
0.42.
Mm-mm. What do we do when we find a z? What do we do with it?
Okay.
I flip it.
We find it in the formula.
Right. Look it up, right? So what is 0.58?
Wait, why do you put?
So 1 minus 0.58,
Mm-hmm.
0.42.
It is? I don't even know. Let me see.
What do you go to, Bob?
So you go to 0.5, then you go across to the 8.
7.57. Am I looking at the
Wait,
right-
1 minus 0.58? Yeah,
No.
What did you get?
Five.
Point what?
0.7104.
Say it again? Yeah.
but I'm doing what you said here though.
Yeah. So look it up in the table like this, right?
No, before I find the Z, then she flipped it, 1 minus
Uh-huh.
P times Z.
Right.
So I gotta times,
No more
Wait.
times. You look up the 0.58 in the table.
I put that in.
Right. Yeah.
Oh,
So this is 0.5 right here.
0.58, okay, so
And then this
that's
is
5.
8 up
right?
here. And then where do they intersect that? Right here.
0.5, you said that?
Yeah,
So
no, that's it.
7088.
No. 0.5 and then the 8 up top. So 0.5 and an 8.
0.5.
Go and then go across the 8. Yeah.
Why is it 8
Yeah.
again? Because that's, we want what's higher, 801.
No, because that's what the number came out to be.
Because
Yeah.
it was 8.
Is it? Yeah.
And then we go up 8.
Oh, so this decimal,
Yeah.
you always wanted the 0 point, that's this one, and then the
Right.
last number is always gonna be.
At the top.
Yeah.
Yeah.
Okay.
And then that's
It's the
closer to
hundredth,
the
right?
first.
100th, right? What happened?
Oh, I get it.
It's closer to the first one.
So if it was
Well, let's see.
0.59 or 0.55,
So,
it
mhm.
would be 0.55.
And then 5 up top.
Okay.
What is it again? 7, 9, 7190, right?
Yes.
7190, right?
Now we're gonna do P times 7, wait, 0.7190, right?
Well, now we just do a little subtraction. Nothing crazy.
But like you see how you said we have to plug it back in, can I just plug
Mhm.
that decimal back in?
Yeah, that's it. So,
Right.
yeah. So this is 0.281. This looks a lot closer than what we got before. All right. So let's take a look back at what the calculator gave us. Just to recap.
0.28.
So this is our actual answer. Excuse me, this is our answer that we found. This is our approximated answer. And then this is the actual. It's closer though, compared to what we did before. This is 27349, etc. Right? Compare that to what we had before at 209.
The actual.
If you don't have the actual calculator, you can approximate it using this method.
And like 0.281.
Right.
Right, okay.
So the important thing to remember here is that you have to adjust your x value to accommodate for the change,
And
right? Mhm.
that's this part right here, right? And she said,
The adjustment?
the adjustment.
No, the adjustment was a 7.5, right? This part,
Oh, you went back a little.
right,
So you want us to go always back a little?
right. If it's greater than, you're gonna go back a little. If it's less than, you're gonna go forward a little
Or if
bit.
it's greater than 5?
Yeah. No. Just always 0.5. Yeah, always 0.5. And then if it's greater than, you go back a little bit. If it's less than, you go forward a little bit.
Less than 0.5?
Yeah. Mhm.
So you would do like 8.5?
Right. Mhm. That's it. All right. Y'all have a whole question on that.
I mean, let me write the actual answer down.
I got you. I have it written on the side here so you can copy it. Hold on. I got you. I'll make it bigger. It's okay. There you go. That's the actual and the approximated.
The 9,
Mm-hmm.
1 9.
Yeah.
Are we gonna learn one more thing after this?
Mm-hmm.
I'm not sure.
But it's far easier than what we've been doing. Yeah, we're good.
So the answer to this was all of this.
The answer is it's 2.81.
I'm saying,
Mm-hmm.
all this whole stuff that we just did,
Mm-hmm.
See, but
from the radicals to the.
Mm-hmm. All of that.
what word, what's the answer in what word?
The answer is looking for is the
The actual.
not the actual, no, the approximated one. The 2.80, yeah. But the first answer wouldn't work because we didn't do the right. Mhm.
What's the first answer?
The 2.09. Yeah. I just wanted y'all to see like how they compare, you know? But let's look at a nicely written solution to this, shall we? All right. So in this example, n is 25, p is 0.25. So the figure represents the probability distribution we will use. Let R be the binomial random variable corresponding to the number of successes out of n equals 25 trials. We want to find the probability of R greater than or equal to 8 by using a normal approximation. This probability is represented graphically here by the area of the bars over 8 plus the area of all the bars to the right of the bar over 8. All right. So boom, this is the x equals 0.75 that we found, right? This is a graphical representation of it. All right.
On the test, if we're gonna ask her to improve this stuff.
Mhm. It'll be clear on the test what to do.
Professor, what's his name?
Huh?
That guy, Google. Is he still around?
You got the highest grade.
That's why he's not here.
Mhm. Yeah. So let X be a normal random variable corresponding to a normal distribution with mu equals n times p, which is 25 times 0.25, which we found is 6.25. And sigma is equal to the square root of n times p times q, which is equal to the square root of 25 times 0.25 times 0.75, which is a 2.17, right? So this normal curve is represented by the red line in the figure. The area under the normal curve from x equals 7.5 to the right is approximately the same as the area of the bars from the bar over r equals 8 to the right. It is important to notice that we start with x equals 7.5 because the bar over r equals 8 really starts at x equals 7.5. The areas of the bars and the areas under the corresponding red normal curve are approximately equal, so we conclude that the probability of r greater than or equal to 8 is approximately equal to the probability of x greater than or equal to 7.5. This is what they're talking about, right? You remember when we did the histogram? All these numbers right here for the binomial distribution they're like midpoints, right? So 8 is like in the middle of this bar. But remember when we first did histograms, we used to use the class boundaries for them, and it would be like a range from this number to that number. So the range here is actually 7.5 all the way up to 8.5, and 8 is in the center of that, right? So that's why we're pulling it back to 7.5 to get all that nice approximated area, right?
So,
Mm-hmm.
how long is 25 working years gonna last? Go back to the question.
Oh, the question?
How was that 0.21?
So that answer that we found, right? That's the chance that the water heaters from whatever that company's name is, right, will last 10 or more years. Mhm. Yeah. Yeah. So you could figure that what, a fourth, a little bit more than a fourth, almost a third of the machines that she buys will last 10 or more years. Yeah. I think it's a bad investment. Like 5 years for a water heater, that's it. Is that even true? Like I don't own a house, but is that true? I don't even know. If it is, that sucks. Like that really sucks. Mhm. All right. So when we convert x equals 7.5 to standard units, blah, 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 we get 0.58. So we have the probability of x greater than or equal to 7.5 is equal to the probability of z greater than or equal to 0.58. We do the complement of that, so 1 minus 0.58, which will give us a 0.281, right? So how does this result compare with the result we can obtain by using a formula for the binomial distribution? Let's take a look. They just use a little calculator to do this, right? What I'm going to show y'all. It's not too bad. Doing office hours after class if anybody wants to stick around. Your choice. All right. So, here's the solution. So using the binomial distribution functions on your calculator, pop, 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 you can get it equal to 0.2735. This means that the probability is approximately 0.27 that 8 or more of the water heaters will last at least 10 years. All right. So how do these results compare? The error of approximation is the difference between the approximated normal value, which is what we found, 0.281, and the binomial value, which is 0.2735. The error is only 0.0075, right? You get that by subtracting the two numbers from each other, right? Which is negligible, right? For most practical purposes. We knew in advance that the normal approximation to the binomial probability distribution would be good since n times p is equal to 6.25 and n times q was 18.75, right? And they are both greater than 5, right? So these are the conditions that assure us that the normal approximation will be sufficiently close to the binomial probability for most practical purposes. Remember that when we use a normal distribution to approximate the binomial distribution, we're computing the areas under the bars. The bar over the discrete variable r extends from r minus 0.5 to r plus 0.5. This means that the corresponding continuous normal variable x extends from r minus 0.5 to r plus 0.5. Adjusting the values of discrete random variables to obtain a corresponding range for a continuous random variable is called making a continuity correction. All right. That's your vocabulary word for the day, continuity correction. All right. Webster's dictionary, here we come. Mhm. All right. I feel like that was a bit much, so let me just give y'all the procedure real quick. Just want to sum it up a little bit, make it a little bit easier. Yeah. Appreciate it. Thank you, man. All right. So how to make the continuity correction right here. So first you convert the discrete random variable r, number of successes, to the continuous normal random variable x by doing the following, right? If r is a left point of an interval, subtract 0.5 to obtain the corresponding normal variable x. That is, x is equal to r minus 0.5, right? If I ask you greater than, you're going to subtract 0.5, right? If r is to the right of an interval, right, add 0.5 to obtain the corresponding normal variable x. That is, x is equal to r plus 0.5. If I ask you less than, add 0.5 to it. All right? So if it's less than, right, add 0.5. If it's greater than, subtract 0.5.
If it's greater than subtract.
If it's greater than, right, subtract 0.5. If it's less than, add 0.4, right? Yeah. So for instance, the probability of 6 less than or equal to r less than or equal to 10, right? So remember, that's in between 6 and 10, right? So where r is a binomial random variable, right, would be approximated as what? I'm between 6 and 10. I want to go a little bit more over here. 5.5, 10.5, right? Make it wider, right? Where x is the corresponding normal random variable.
So because it's less than, you
Mhm.
add one.
Right.
Because it's 5.5 less than x less than 10.5. Have to add 0.5.
Right. And then let's look at the reason why real quick. Using this example. So here we go. All right. I have a binomial distribution. I'm trying to approximate to a normal distribution, right? I want the probabilities from 6 to 10. All right. I want 6, 7, 8, 9, 10. Right. But I want to use the normal distribution to approximate the answer, right? So rather than just being at 6, I'm going over to the border of 6, which is 5.5. And then rather than being at 10, I'm going over to the border of 10, which is 10.5. And then I will do what you know how to do, change it to a Z, look it up in the table, subtract the two answers, boom. That's it. All right. Nothing crazy there. So y'all could take a look at that for homework. Mhm. I see. Mhm. That's a good question. I don't even know. 7 point something. Hmm.
And area under the standard normal distribution.
No, this is a normal approximation to a binomial distribution. So what does a normal approximation to a binomial tell us, right? A normal distribution can be used to approximate the probability of R successes out of n binomial trials in order to use the normal approximation. Excuse me. The products n times p and n times q must both exceed 5, where n is the number of binomial trials and p is the probability of success on a single trial, and q is equal to 1 minus p. Unless n is fairly large, a continuity connection may be necessary in order to improve the approximation. Right? And we saw what happens when we don't do that. All right. So we'll talk about this. All right. I'm gonna briefly talk about something real quick and then jump into another topic. Yeah, that's more important. You do not have a homework question on what I'm about to talk about. I'm just talking about it so that you guys can know about it. Okay. So you have experience, you know? That way when you're in grad school, like, they can't fool you. Right? All right, so this next topic is called sampling distributions for proportions. All right. Again, you don't have a homework question on this. I'm just talking about it for you to know about it. All right. So in the previous sections, we studied the sample distributions for the mean. Now we have the tools to look at sampling distributions for proportions. Suppose we repeat a binomial experiment with n trials again and again, and for each n trial, record the sample proportion of successes, right? This is what's called p hat, right? Which is equal to r, the number of successes, divided by n, which is your sample size, right? The p hat values form a sampling distribution for proportions, right? So here you go. This is the sampling distribution for proportions. P hat is equal to r over n. Given that n is equal to the number of binomial trials, a fixed constant, r is your number of successes, p is your probability of success on each trial, q is your probability of failure, which is 1 minus p. If n times p is greater than 5 and n times q is greater than 5, then the random variable p hat, which is r over n, can be approximated by a normal random variable x with mean and standard deviation. Now, this is different about this one now, right? So the mean for p hat is equal to p, right? Whatever p they give you. The standard deviation for p hat, this is a different formula now, is the square root of n times p divided by, the square root of p times q divided by n. That's what I meant to say, right? So the standard error for the p hat distribution is the standard deviation sigma p hat of the p hat sampling distribution, right? So you continue. Mhm. I'm just giving you some information. That's all. Just information.
How do you remember these things, Professor?
I use a formula sheet. I use a formula sheet. I remember everything. Yeah. Even when I'm in, I see, even when I'm like in tutoring and stuff, I take out the formula sheet and I just look it up when I don't remember something. Yeah. All right, so let's make a comment about this, right? So obtain the information regarding the sampling distribution for the proportion p hat equal to r over n. We consider the sampling distribution for r, the number of successes out of n binomial trials. Earlier, we saw that when n times p is greater than 5 and n times q is greater than 5, the r distribution is approximately normal, with mean mu for r is equal to n times p and standard deviation sigma for r is equal to the square root of n times p times q. Notice that p hat is equal to r over n is a linear function of r. This means that the p hat distribution is also approximately normal when n times p and n times q are both greater than 5. See you later, man. So in addition, from our work in section 6.1 with linear functions of random variables, we know that the mean of p hat is equal to the mean of r hat divided by n, which is equal to n times p divided by n, which is equal to p. And the standard deviation for p hat is equal to the standard deviation of r over n, which is equal to the square root of n times p times q divided by n, or the square root of p times q divided by n. Although the values r over n are discrete for a fixed n, we do not use a continuity correction for the p hat distribution. That's something different, right? We don't use that continuity correction there. So this is the accepted standard practice for applications in inferential statistics, especially considering the requirements that n times p is greater than 5 and n times q are met. We see from the sampling distribution for proportions that the mean of the p hat distribution is p. The population proportion of success, this means that p hat is an unbiased estimator for our p, right? For our probability. So what does the p hat sampling distribution tell us? Consider n binomial trials. We use p hat equal to r over n to estimate what our proportion p will be, right? The population probability of success on a single trial where r is the number of successes out of n binomial trials. To create a p hat distribution, repeated sets of n binomial trials must be conducted to determine individual sample statistics p hat. Fortunately, mathematicians can be used to obtain mathematics, excuse me, can be used to obtain the following information. For n times p greater than 5 and n times q greater than 5, the p hat distribution is approximately normal. The mean of the resulting p hat distribution is p. The standard deviation, also known as a standard error, is a square root of p times q over n, where q is equal to 1 minus p. All right? And then I got you. I do have an example. Would you guys like to see that? Or no? You want to see the example? All right. I think the example will make more sense. It is? No. It's just information. It's also not on your homework either, you know? Just so that you know. You okay?
Higher. Schedule class says.
Not necessarily.
Be right early to go.
Nah, not necessarily. Just take it to tutoring, and I'll give you half the points back that you missed. No problem.
Got 15. So we're gonna say about it again.
A lot. A lot. Yeah. Remember what I said though, right? The formula for B, all you need to do is just get you a little 50 on all the tests and you're good. And 100 on the homework. And 100 on the homework. Yeah. All right, let's look at this example real quick, right? Now, let me give you an example, then it'll make more sense, all right? Look, sampling distribution of p hat, right? The annual crime rate in the Capitol Hill neighborhood of Denver is 111 victims per 1,000 residents. This means that 111 out of 1,000 residents have been a victim of at least one crime. For more information, you can go on the website, whatever. These crimes range from relatively minor crimes, stolen hubcap or purse snatching, to major crimes, which is like murder, right? The Arms is an apartment building in the neighborhood that has 50-year-old residents. Suppose we view each of the n equals 50 residents as a binomial trial. The random variable R, which takes the values of 0, 1, 2, 3, all the way up to 50, represents the number of victims of at least one crime in the next year. So, question A, what is the population probability P that a resident in the Capitol Hill neighborhood will be a victim of a crime next year? And what is the probability Q that a resident will not be a victim of the crime, right? So using the report, right? Our probability of you being a victim of the crime is 111 divided by 1,000, or 0.1111, right? The probability of you not being a victim of the crime, right, is just the Q, the probability of failure. So 1 minus the 111 over 1,000, which is 0.889. Simple, right?
So what's the N?
N is your the 1,000. Yeah. R. So that's when you're talking about the people in the building, that's R. That's the number of successes. Like that's the success is you being part of a crime, you being victimized of a crime, right?
All those people.
Right.
X amount.
Like instead of us looking at 1,000, we're only looking at the people in one building, right? But the chance that there'll be a victim of a crime is out of the whole city of 1,111 divided by that. All right.
How do you fix timing for something? For real, with everything you know, I want to be sure grading on.
Just keep practicing.
Like,
Little experience and keep practicing. But it's cool though, right? Thank you. You'll be too, don't worry. When you're done with like grad school, you're a whole nurse practitioner, it's gonna be fine.
I'm not gonna go. We're gonna have a bonfire.
Will you be kind to
everything is there.
you need that because you gotta look up things in real time, like how do you help your patients. Mhm. All right, so look at this. Consider the random variable p hat, which is equal to r over n, which is equal to r over 50. Can we approximate the p hat distribution with the normal distribution, right? So first we have to verify if n times p is greater than 5, right? And n times q is greater than 5. So 50 times 0.111 is 5.555. 50 times 0.889 is 44.45, right? So since both n times p and n times q are greater than 5, we can approximate the p hat distribution with the normal distribution, which we know how to do, right? So what are the mean and standard deviations for the p hat distribution, right? So remember the mean is going to be the same thing as the p, right? No, no, it's just the 0.111.
That's the mean
Uh-huh,
and the standard deviation.
right. So there you go, right? So the mean for p hat, we said is the same thing as p, which is 0.111. However, the standard deviation for p hat is going to be the square root of p times q over n. Just plug it in. No, we did that already. That one was up here. That was this one right here.
That point, I'm sorry.
Oh, I got you. I got you. So the P is 0.11 and Q is 0.889 over 50. This is just a little calculator, right? And then you get 0.044, right?
Wait, divided by 50, right?
Yeah.
I'm like, wait. Oh, I didn't even do the.
Mhm.
So when we look at a problem like this, we just think of this point,
Right.
but how do we get 0.111? Like,
So that was given in the story, right? Yeah, so we knew in this neighborhood, 111 victims, right, were vandal victimized, whatever, out of the 1,000 residents that live there. So that's the 111 divided by 1,000, right?
The rest of the square root is just, and that number times itself.
The square root of, yeah, and so 0.111 times, oh, like what is the square root?
Yeah,
It's the inverse of an exponent. So if I say like 5 to the second power, right?
square root of 5 would be.
Well, no. 5 to the second power means 5 times 5, which is 25. But if I say what's the square root of 25, I'm asking you what number times itself gives you 25, and that's 5. Yeah, so
No, I
square.
was just saying that, but I
Yeah.
couldn't find variable time.
Oh, I got you. Just turn it sideways. Yeah.
No, it is.
Yeah.
The thing is,
It's like square root X. That's what it is. So if you type in like 25 and then hit that, it'll give you 5.
right?
Yeah.
0.111.
For P, yes.
That's P, and
Yeah.
Q is,
Q is 1 minus P. So 1 minus the 111 over 1,000.
Over one,
Right.
so what,
What's what?
what do you mean over? What does that mean?
Like divide?
I did the part.
Yeah. Yeah.
Equals 0.111.
Yeah. But Q is 1 minus 111 divided by 1,000. Yeah.
Minus. What?
No. 1 minus 111 over 1,000. 1 minus over 1,000. Yeah. Minus 111 over 1,000.
You gave me 88.9.
That's it.
Straight into a.
No, that's good.
So.
It should be 0.889.
Yeah, I
Yeah,
tended it.
yeah. Mhm. Now, they didn't ask you a question here, but they could ask you something along the lines of,
That. This solution. So this is how we went.
yeah. Now, in this question, they could have went a little bit further. They could have said, oh, what's the probability that 5 out of the 50 people, for example, would be victimized or something, right? Then you would use the normal distribution to approximate it. But I'm telling you, this is your mean, and this would be your standard deviation. So you just need to figure out what the P is, and then
And the
if
word
and if
problem.
it's greater, right, if it's greater than or less than, and then just do what you know how to do after that.
That's my problem, how to distinguish in the word problem what's what.
I got you.
Like,
But as I said, this is just knowledge. This is not on your homework. It's not on your tests.
like, I'd rather you just give us
Yeah.
NQ and P.
Always.
No,
Yeah.
you write it in a word problem, then we
Yeah.
gotta figure out which ones, and
Yeah.
that's what confuses me. I'd rather just have it highlighted.
Right.
Well, this one in this question, it doesn't give you P flat out, but it does give you N and it does give you R. On the,
But it's
I don't know.
confused, and we do a whole calculation, wrong N and P.
Yeah.
Like,
Let me
I don't know who well with word problem.
I got you.
So we're never gonna use that?